Hi everyone. I'm here to discuss topic on open source database architecture for high volume financial analytics. Financial analytics platform face unprecedented data challenges, processing millions of transactions while delivering real-time insights. Open source database systems have emerged as the backbone of modern fintech analytics, enabling organizations to scale cost effectively while maintaining full control over their data architecture. Now, let's see the data imperative in modern finance. Right, so traditional monolithic database system, once the bedrock of daily batch processing, are now buckling under the relentless pressure of modern financial demands. High frequency trading floors pulse with thousands of transactions per second, each demanding instantaneous risk assessment, while globally payment processor orchestrate an insistent 24 per 7 deluge of transaction, especially after crypto. This isn't just about escalating data volume, it's a paradigm shift, fundamentally reshaping the very infrastructure financial institutions rely on. Insights that once gestated overnight must now explode forth in mere seconds, transforming the leisurely pace of yesterday into today's urgent imperative. In this rapidly evolving environment, institutions that swiftly adapt to these data challenges gain significant competitive market advantage, turning legacy systems into critical liabilities for those unable to keep pace. So, why we have to go to open source databases? First, there is complete transparency. Full visibility into system behavior enables deep understanding when milliseconds matter. Right. So, freedom from lock-in, preserve flexibility as business requirements evolve without vendor constraints. Vibrant communities. The open source database communities are active. There is a lot of innovations happening over there, and the bug fixes are rapid, driven by global developer ecosystem. Massive scalability. Horizontal scaling across commodity hardware matches or exceeds proprietary solutions. So let's dive into modern financial analytics architecture. Financial analytics architecture have evolved beyond simple data warehouses. Modern systems must simultaneously support multiple workload patterns, trading analytics demanding microsecond latency, risk management requiring consistent snapshots, compliance needing immutable audit trails, and customer dashboards expecting responsive performance. This has driven a fundamental shift towards polyglot persistence strategy, using multiple databases instead of one within a single platform, each optimized for specific workload characteristics. So we will review um, some of these technologies, these multiple technologies. The polyglot persistence stack, what we are going to talk about is operational database. Postgres is an example which can handle transactional workload with ACID guarantees, ensuring accurate record of every data, payment, and account update. Then streaming pipelines are there. Apache Kafka is one example, provides durable message buses that capture change streams, route events, and maintain ordered transaction logs. Analytical database, ClickHouse and Cassandra excel at complex queries across massive datasets with specialized storage optimization. Then there is caching layers. Redis provides microsecond access to frequently queried data like real-time prices and computer risk metrics. Let's first discuss the Apache Cassandra distributed write performance for financial events. Ultra low latency write performance is paramount in financial system. Instant and reliable recording of trades, market orders, and payments prevents significant financial losses, regulatory non-compliance, and loss of trust. Robust write capabilities are essential for core banking, trading, and fraud detection platform. Cassandra's masterless peer-to-peer architecture is designed for high-throughput distributed writes. Data is partitioned across replicator nodes, allowing writes to be processed concurrently. This distributed nature eliminates contention and provides linear scalability perfectly suited for every growing financial event streams. This architecture offers tangible benefits. Financial institution can process millions of transactions per second, support massive global trading volumes, and enable real-time anomaly detection. High availability and fault tolerance ensure critical operations remain uninterrupted even during node failures, meeting strict industry reliability demands, making Cassandra as one of the good candidate. Cassandra's decentralized architecture. Cassandra's architecture treats all nodes as equal. Any node can accept write, which it then replicates according to configured replication factor. This eliminates single point of failure and enables massive write throughput by distributing workload across the entire cluster. A major exchange might generate millions of price updates per second. Each price tick, order book update, trade execution becomes a write to Cassandra, which distributes these writes using consistent hashing without degradation. So tunable consistency in Cassandra, powering diverse demands, right? Quorum, unyielding data integrity. When absolute certainty is paramount, especially for financial transaction, quorum ensures robust data integrity. The majority of replicas must acknowledge rights, guaranteeing the strongest consistency for mission critical financial transaction, even if it means a slight increase in latency for unmatched reliability. The next one is one blazing fast ingestion. For scenarios demanding lightning speed, one optimized for maximum throughput. A single replica acknowledgement facilitates rapid, high volume data ingestion, ideal for capturing real time market data, where eventual consistency is a strategic advance for unparalleled performance. Local quorum, global reach, local speed. Navigate the complexities of globally distributed system with local quorum. This consistency level provides a shrewd balance, delivering strong consistency within a data center while optimizing performance across global region, ensuring both reliability and responsiveness for worldwide operation. Time series excellence. Market data, transaction logs, and user activity all exhibit append-only characteristics with time-based access pattern. Cassandra's log structured merge tree storage engine excels at these workloads, buffering writes in memory before flushing to immutable disk files. Compaction processes continuously merge files, maintaining query performance even as data volume grow into the petabyte range. A time series table might partition by instrument and day, then cluster by timestamp, enabling efficient retrieval of all price updates for specific securities within time ranges. Next, we will see the Postgres plus Citus relational power meets horizontal scale. Despite the rise of NoSQL database like Cassandra, traditional relational database still plays role, remain foundational in finance due to their strong consistency, data integrity, and complex query capabilities. Financial transaction, regulatory reporting, and audit trials demand the rigorous asset properties that relational models inherently provide, ensuring accuracy and reliability. Citus transforms Postgres into a distributed relational database, enabling horizontal scaling for high throughput financial workloads. It routes data across multiple nodes while maintaining full SQL functionality and transactional guarantees, allowing financial system to grow from gigabytes to petabytes without compromising data consistency. This combination offers financial institutions a robust platform for real-time analytics, risk management, and regulatory compliance. It leverages PostgreSQL's rich feature set and extensibility, augmented by Citus distributed architecture to manage vast data sets with both relational integrity and the performance required for modern financial applications. The other advantage of using Citus distributed PostgreSQL is Citus extension transforms Postgres into a distributed database, enabling horizontal scaling while preserving the relational module and SQL interface developer can understand. A coordinator node receives the queries and plans execution across worker nodes, storing the actual data. The architecture maintains Postgres rich feature set, complex join, window function, JSON operators, while enabling linear scalability through worker node addition. So the application code works unchanged against Citus cluster. You automate routing and result aggregation across worker node, add workers to increase capacity without architectural change. Now the different sharding strategies for financial data we can review, which can unlock the performance and precision. First, the customer ID personalized precision unleash rapid access and ironclad isolation for each client portfolio by sharding account data by customer identifier. We ensure lightning fast single customer queries and robust tenant isolation, critical for personalized financial services and security. Then the instrument symbol, real-time market mastery. Revolutionized real-time market analysis. Sharding market data by security symbol enables massively parallel processing across diverse financial instruments, delivering instantaneous insight for agile trading and strategic decision. Transaction-based optimized historical insight. Master of the vast ocean of historical data, parsing records by transaction date, streamlines time range queries, empower regulatory compliance, and optimize data lifecycle management for critical financial archiving and profound analytics. The columnar storage for analytics. Citus columnar storage extension significantly optimize analytical queries, efficiently scanning large datasets while selecting only relevant columns. This capability is crucial as financial institutions often utilize both row and columnar representative of the data. Columnar storage organize data by column, make it exceptionally efficient for analytical workloads. By storing values from the same column together, it enhances data compression and minimizes disk I/O as only necessary columns are read. This design dramatically accelerates queries for tasks like analyzing market trends or a portfolio performance. Financial institutions commonly adopt a dual storage strategy. A row-oriented database excels as transactional processing, handling individual client rates and account updates. In contrast, column storage is deployed for analytical processing, enabling rapid, complex queries on large datasets for business intelligence and data warehousing. This hybrid model balances real-time operation with deep analytical insights. The benefits for financial analytics are substantial. Columnar storage accelerates critical operations like calculating market aggregate, generating comprehensive regulatory reports, and performing compliance checks on vast historical data. This leads to faster fraud detection, improved adherence to regulation, and quicker insight for financial analysts, enhancing overall decision making. Now let's look at the ClickHouse columnar analysis for financial time series. ClickHouse is exceptionally well suited for financial time series data due to its columnar storage and vectorized query execution. These features enable rapid aggregation and filter of vast historical datasets, which is crucial and for analytical trends, pattern, and anomalies in time-stamped financial events, even for AI, from trade data to market movements. High-performance capabilities allow financial analysts to query terabytes of data in sub-second times. Its architecture effectively handles the massive scale and velocity inherent in financial market data. ClickHouse leverages high-ratio data compression and parallel processing across multiple CPU cores to ingest millions of data points per second while maintaining low query latencies. This resilience ensures that even during peak market activity, the platform can process and analyze real-time data stream without performance degradation, making it ideal for dynamic financial environments. Key use cases for ClickHouse in financial institutions include real-time risk analytics, enabling immediate assessment of portfolio exposure and market volatility. It also excels in market surveillance, identifying suspicious trading patterns and potential fraud as they occur. Furthermore, its ability to quickly query large datasets makes it invaluable for comprehensive regulatory reporting, ensuring compliance with strict financial regulation by providing auditable and timely data insights. Why ClickHouse excels at financial analytics? First, as we discussed, it's have a columnar storage. Values from the same column stored contiguously enable dramatic compression query performance. Query scanning specific column to read only relevant data from disk. Then aggressive compression. Specialized codecs for different data types achieve remarkable ratios. Financial data patterns, predictable timestamps, cluster prices compress exceptionally well. Real-time ingestion, batch inserts balance latency and throughput, buffer incoming events for seconds, then insert in batches achieving massive throughput with acceptable latency. Materialized views, pre-compute aggregations and enable real-time analytics. Views incrementally update as new data arrives, providing instant query response. Query performance at scale. At the core of ClickHouse, unparalleled query performance for vast time series data sets lies the ingeniously designed merge tree table engine. The powerful engine leverages a meticulous data organization strategy. The primary key dictates the optimal sort order, ensuring lightning fast filtering and lookup operation, while the partition key intelligently segments data into manageable physical files, dramatically accelerating scan operation across colossal volumes. Consider a critical financial market data table where partitioning by month and setting a primary key on instrumental symbol plus timestamp isn't just a best practice but a game changer. This precise configuration enables analysts to execute complex queries like retrieve all trades for this specific symbol within crucial time range with breathtaking speed. We are talking about sub-millisecond response time across billions of rows, empowering real-time risk analysis, instant trade reconciliation, and immediate fraud detection. ClickHouse transformed what was once a batch processing challenge into an interactive real-time advantage, directly impacting strategic decision-making and operational efficiency in high-stakes financial environments. So data pipeline architectures. In the relentless current of modern data, robust pipeline and architecture are not just beneficial, they are indispensable. At the heart of this dynamic system, Apache Kafka emerges as the crucial central nervous system orchestrating the seamless flow of information. Operational database, the very pulse of business activity, publish their change streams to Kafka, feeding every transaction, event, and interaction into a unified real-time stream. The raw data is then channeled through powerful streaming processor. These intelligent engines transform, enrich, and aggregate data in flight, performing complex computation and cleansing operation millisecond and event occur. The real-world impact is profound, from enabling sub-second fraud detection and dynamic personalized customer experience to powering proactive operational insights and real-time market responses. These advanced data pipelines empower organizations to move beyond reactive analysis, transforming raw data into actionable intelligence at the speed of business, driving agility, resilience, and a significant competitive advantage. So we extract the data. Debitum capture every insert, update, delete from operational database with minimal performance impact. Then Apache Flink enriches transaction with customer data, applies fraud rules, aggregate balances in real time, then processed event flow into specialized database optimized for their query patterns. Exactly once processing semantics ensure each event process exactly once even during failures. Kafka transaction combined with stream processor checkpointing provide reliability financial institution trust for mission critical data movement.